Our next speaker is Takahiro Nishinaka, and he will tell us about two-dimensional crystal melting and D4-D2-D0 on toric Calabi-Yau singularities.
Thank you. So first, I'd like to thank the organizers of this nice conference for giving me a chance to talk about my work today. So today, I'd like to talk about the relation between the two-dimensional crystal melting and the D4-D2-D0 bound states on toric Calabi-Yau singularities. And this talk is based on this paper with two collaborators in Japan. So let me first explain my motivations. So the crystal melting model is a kind of statistical mechanical model which was proposed for D-brane counting. For example, when you consider the D62-D0 bound states on a toric Calabi-Yau singularity, then the BPS index of the D-brane bound states is evaluated by counting molten configurations of a three-dimensional crystal like this. I'm sorry about this, not a good color. I use the orange, but it's not good, sorry. So three-dimensional crystal. And so this is an example of the conifer. This is an infinitely extending, pyramid-type crystal composed of blue and green atoms. And if you consider all the meltings of this crystal, then you can evaluate the BPS index of the D-brane bound states on a conifer, for example. And moreover, if you consider the limit shape of the crystal melting crystals, then you have an information about the smooth geometry of the mirror Calabi-Yau 3/4. So in this sense, the crystal melting describes some discretization of the background Calabi-Yau geometry. If you take the limit shape, you have a smooth geometry, but before taking the limit, you have a discretized crystal like this. So this is a physical idea and motivation. And also, this topic is closely related to, again, orange, I'm sorry about this. It's closely related to non-commutative Donaldson-Thomas invariance. It's a mathematical topic, and it's a kind of topological invariant of the Calabi-Yau 3/4. And this topic is closely related to crystal melting model. So what I want to say here is that crystal melting is interesting, both in physics and mathematics. And today I'd like to talk about some generalization of this story to D4-D2-D0 states. So I'm going to replace this D6 brane with a D4 brane, which is non-compact and wrapping on some toric divisor of the Calabi-Yau 3/4. Then you get the two-dimensional crystal melting model rather than this three-dimensional one. So that's what I want to talk about today. So in the first half of my talk, I'm going to review this D62-D0 crystal melting first. And after that, I'm going to talk about my own work about the D4-D2-D0 generalization. So let me first review the D62-D0 crystals. So for example, if you have a conifer as a toric Calabi-Yau 3/4, then we put a single non-compact D6 brane. This is a non-compact D6 brane, and we only consider a single D6 brane wrapping on the whole Calabi-Yau or whole conifer. And we put a lot of D2 branes, wrapping on some vanishing 2-cycle of the conifer. And you also consider the D0 branes, many D0 branes, which are point-like in the Calabi-Yau or conifer. And the question is, what is the BPS index of these D-brane bound states? And so these D-branes are extending in this Calabi-Yau direction, of course, but they are also extending in one more direction in this 4-dimensional spacetime. So if you dimensionally reduce this Calabi-Yau direction, then you get the BPS particle. These D-branes are regarded as BPS particle in these 4 dimensions. And on the world line of the BPS particle, we have D equal 1, N equal 4 quiver quantum mechanics. Supersymmetric quantum mechanics. So we want to calculate the BPS index of these D-brane bound states, but let us see what the effective theory is living on this world line of the BPS particle. So this is a D equal 1, N equal 4 quiver quantum mechanics, but it's a dimensional reduction of the 4-dimensional N equal 1 supersymmetric theory. So the theory is characterized by quiver diagram and the superpotential. And the quiver diagram is a slight modification of the Klebanov-Witten-Strassler type quiver diagram. And the modification is due to this existence of this D6 brane. So this white node is associated with a D6 charge, a single D6 charge. So we assign the U1 gauge group to this white node. And blue and green nodes are associated to this D2-D0 charges. So this is a slight generalization of the Klebanov-Witten type quiver. And the superpotential is exactly the same as the Klebanov-Witten type potential. And the question is, what is the BPS index? But in terms of the effective theory on the D branes, BPS index is equivalent to the Witten index of the theory. So our task is to evaluate the Witten index of this quiver quantum mechanics. So that's what I want to do. And Witten index is roughly, up to sign, equivalent to Euler characteristic of the moduli space of vacuole. So what we have to do is to identify the moduli space of vacuole first and calculate the Euler characteristic of the moduli space. And it's a very complicated task, but in principle, we can do that. And I'm not going to talk about the detail today, but we can do this explicitly. And the result is very interesting. When you define, I'm sorry about this orange letter, but if you define the generating function of the Witten index, Z, omega is a Witten index, and the Witten index depends on the D-brane charges because rank of the gauge groups are depending on these D-brane charges. So omega is a function of D-brane charges, and especially a function of D2 charge and the D0 charge. So we introduce fugacities, a small q and capital Q, for the D2, D0 charges, and take a summation over all the D2, D0 charges, and define the partition function or generating function. And if you calculate this generating function for the conifold case, then the result is very interesting. Result is written as a sum over crystal melting of this pyramid type crystal. And here by melting, removing atoms from the top of this pyramid. So what we can do is first we can remove this top blue atom, and the next we can choose two green atoms. We can remove this green atom or this green atom. We have two options, something like that. And there is an infinite number of ways of removing atoms. So this summation runs over all such melting or all such removing atoms. And this exponent of small q and capital Q depends on the number of atoms which you removed. So for example, we have 1 corresponding to removing nothing. And the next term is associated to removing only top blue atoms. And if you substitute these numbers, then you get this factor. And second one is removing only a single blue atom and a single green atom. And we have actually 2 such contributions. So we have 2 such contributions into the partition function. And we have to sum up all the terms. This is an infinite sum. And very interestingly, if you sum up all the terms, then you get this interesting product. This was studied by Zendro and Young mathematicians about 5 years ago or something. So my message here is that when you calculate this generating function of the Witten index, then you always have this interesting sum over melting crystal. And if you consider D6, D2, D0 states, then you always have 3-dimensional crystal melting. That's the general property. And let me here stress that the structure of the crystal depends on the quiver diagram. For example, this is one example of a melting crystal. And we have 2 different kinds of atoms, blue and green atoms, right? And that 2 different kinds of atoms are corresponding to 2 blue and green quiver nodes in the quiver diagram. And let me ignore white one for now for some reason. And also in the crystal, we have many atoms, but the blue and green atoms are attached to some point. And at some point, for example, if one blue atom is attached to one green atom, then we say that there is a bond between these 2 atoms. 2 atoms are connected by one bond. And actually, these bonds are corresponding to these bifundamental field. So what I'm saying is crystalline structure depends on the quiver diagram of the quiver gauge theory. And this quiver, of course, depends on the Calabi-Yau threefold. So if you change Calabi-Yau 3-4, then you have a different crystal melting. Okay. Yeah.
There was a paper by Tron and Jeffries on the conical, and they had a different.
Okay, that's a good question. That's about the wall crossings, right? That's about the wall crossings.
Yeah, but the paper they wrote, so the additional non-fluidity.
Right, you're right. Yeah, you're right. You're right. So here I'm picking up some special value of Kähler moduli of background conifer, and with such moduli parameter, we have this quiver diagram without with only one arrow from white node to blue node. But if you change the Kähler parameter, I mean, if you blow up the 2 cycles of the conifer, then we have different type of quiver. So I didn't talk about the moduli, but yeah, if you change the Kähler moduli, then we have a wall crossings, and correspondingly we have a different quiver, and then that quiver corresponds to the Tron-Jafferes quiver. Yeah, you're right. Thank you. Okay, so that's one thing, and yeah. So I mean, this crystalline structure depends on the Calabi-Yau 3-4 you are considering. And the C3 case, the simplest example was studied by Okunko, Frechette, Kimbacher many years ago, about 10 years ago. This Zenroy studied conifer this example, and these people studied the general toric Calabi-Yau case. So this is a brief review of the D6-D2-D0 case. And our work is about the generalization to D4-D2-D0 case. So what we want to do is to replace the D6 brane into a D4 brane, wrapping on a toric, non-compact toric divisor. So let me talk about the conifer example again. So conifer has 4 different toric divisors, and I'm sorry, I guess this is really hard to see, but we have 4 different toric divisors, and this is a toric diagram of the conifer. And in the conifer case, these toric divisors are isomorphic to each other, so we choose one of them, for example, this lower left one, and we put a D4 brane, single non-compact D4 brane to this divisor. And we consider a lot of D2 branes wrapping on the vanishing 2 cycles, and we consider a lot of D0 branes, point-like in the conifer. And the question is, what is the BPS index of this D brane bound states? And we again consider the BPS particle. So we dimensionally reduce the Calabi-Yau 3-4, and we regard these D brane bound states as a BPS particle. Then what is the effective theory on the world line of the BPS particle? Then we have a slight modification in comparison with the D6-D2-D0 case. I mean, in the quiver diagram, we have an additional chiral multiplet J. This is induced by the D4 brane. You know, in the D6-D2-D0 case, we didn't have any J, but here we have J. And also, due to this J, we have an additional term in the superpotential. You know, these first 2 terms are exactly the same as the D6-D2-D0 case, but the third one is a new one. I guess, I don't know why this is colored by blue, but okay. This is an additional superpotential term induced by the D4 brane. So, sorry? Yeah, that's a good point. Yeah, actually, in the D6-D2-D0 case, D6 brane induces no superpotential. I mean, this potential comes from D2-D0 branes. D6 brane gives nothing because D6 brane is associated to this quiver nodes, right? But in D6-D2-D0 case, we didn't have J. We only have I. So we cannot write down any gauge invariant operator including I because you know, we have to close the trace. So I mean, in the D6 case, D6 did nothing about the superpotential. But in the D4 case, we can write down the gauge invariant operator including this node. So that's why we have this term. Thank you. That's a good question. Okay, so we have 2 differences. And this difference is actually a general property. I mean, when you put the D4 brane on a toric divisor of some general toric Calabi-Yau 3-4, then you always have this type of superpotential. I mean, the first one is the D6-D2-D0 potential, and the second one is induced by the D4 brane. And X0 is a kind of some chiral multiplet included in the quiver diagram. And so our task is to evaluate the Witten index of the quiver quantum mechanics. So we have to solve the F and D term constraints. But this specific general form of the superpotential leads to some nice theorem about the supersymmetric vacuole. And so let me talk about it. So when you choose some special values of Fi parameters, then supersymmetry, F and D term constraints require some conditions. The first condition is J has vanishing wave on supersymmetric vacuole. And the second one is very important and interesting. There is a set of chiral multiplet called perfect matching. And all the chiral multiplet X included in this perfect matching has vanishing waves. So this is a theorem followed from this superpotential, and we can show this probably 15 pages of our paper. So today I have no time to explain this, but I just accept this theorem and see what's happened if you accept this. But before that, I need to talk about what the perfect matching is. So in the next 2 slides, I'm going to talk about what the perfect matching is. And after that, I will talk about what's the results of these 2 constraints. So in the next slides, so let me talk about what the perfect matching is. So the perfect matching is a mathematical object defined in the Daimer model. And the Daimer model is a kind of statistical mechanical model associated to this quiver diagram. So this is an example of the conifold. So we have a quiver diagram on one hand. And for now, let me again ignore the white node. So this is a quiver diagram for conifold. And if you have this quiver, then you also have this type of picture, Daimer model, defined on the 2 torus. This upper edge and the lower edge are identified with each other, and right edge and left edge are identified with each other. So this is a torus. And on the torus, we have 2 Daimer nodes or vertices, yellow and white nodes. And also we have Daimer edges between yellow and white nodes. We have 4 such Daimer edges. 1, 2, and 3, and 4 edges. And what is the relation between these 2? First of all, there is 2 connected regions in the Daimer model. All these blue regions are the same connected one component of one connected component, and these green regions are also one connected component. So we have 2 connected components, and we call them faces of the Daimer model. So these Daimer faces are actually corresponding to these quiver nodes. And also, we have 4 edges, 4 Daimer edges, and they are actually corresponding to 4 chiral multiplet or bifundamental fields in the quiver diagram. So A1 and A2, B1, B2 are associated to these 4 Daimer edges. And what about the Daimer nodes? We have 2 Daimer nodes, yellow and white, and they are actually related to superpotential term. For example, this yellow node is surrounded by A1, B2, A2, B1, and therefore we have trace of A1, B2, A2, B1, and white node gives another term. And the overall sign depends on the orientation of this arrow, orientation of this chiral multiplet. So what I want to say here is that there is a general relation between quiver and Daimer. And the most important thing is each Daimer edge, these 4 edges, are corresponding to chiral multiplet. So this is a Daimer model. And what is a perfect matching? So perfect matching is a collection of Daimer edges so that every Daimer node is attached to one and only one edge included in the perfect matching. So in this conifold case, we have 4 such perfect matchings. So in each picture, this red edge is attached to yellow and white nodes, and every Daimer node is attached to one and only one red edges. So this is a perfect matching. Then let me consider the intersection number between these red edges and green arrows. Green arrows are going in x direction and y direction. Let me consider the intersection number. In this picture, we have no intersection, so we assign 0, 0 to this perfect matching. But in the second perfect matching, we have one intersection between x direction, green arrow, and red edge. But y direction has no intersection, so we assign 1, 0 to this perfect matching. And we do the same thing for all the perfect matchings. Then what is interesting is that these integers, describe the lattice point of the toric diagram of the toric Calabi-Yau 3-fold we are considering. In this case, conifold. And this is a general property. And our claim is that, what is our claim? Our claim is that when you put a single D4 ring on a toric divisor associated with a corner of the toric diagram, then there is always a perfect matching, unique perfect matching associated to this corner. Then supersymmetry, I mean F and D term constraints, requires that all the chiral multiplets included in the perfect matching have vanishing webs. So I mean, in this case of the conifold, again, I missed something. I'm sorry. In this case of the conifold, we put a D4 ring here, right? Then this divisor is associated with this perfect matching, and this perfect matching includes B2. So supersymmetry requires B2 equals 0 on supersymmetric vacua. So this is our claim. And so what happens if you accept this claim? I have no time to give you a proof of this claim, but let me accept this claim. Then what happens? So let me remind you that this is our quiver diagram for D4-D2-D0 states. But we already know that on the supersymmetric vacua, we have J and B2. We already know that J and B2 have vanishing webs. I mean, they are not massless in the vacua. So we have to eliminate these. But as I said before, these bonds of the crystal is corresponding to these chiral multiplet, A1 and A2, B1, B2. So if you eliminate especially B2, then we lose many atoms from this crystal. And the result is like this. You know, these atoms are eliminated because we eliminated B2. Then the remaining crystal is a two-dimensional surface of the original three-dimensional crystal. And this is a general property of D4-D2-D0 crystal melting. And we can re-express this surface, two-dimensional surface, in terms of this bunch of triangles. Then the generating function of the Witten index is written as a sum over the meltings of this two-dimensional crystal. Then the result is like this. It's a kind of generalization of the Young diagram. Then the partition function is, we can show that this sum is rewritten as this product. And what is interesting is that we can show that this product, or this partition function, is consistent with the wall crossing formula of BPS index, which has been recently studied extensively. OK, so this is a conifold example, but we can do this analysis for any toric Calabi-Yau 3-4. So that's a general property and analysis. So I have an infinite, I mean, in principle, I have an infinite number of examples, but today I'm going to talk about the most important examples. I mean, let me consider the orbifold, C2 over Z2 times C. This is one example of toric Calabi-Yau 3-fold, and this is a toric diagram of this Calabi-Yau. And we can put a D4 ring on one of the toric divisors. And for example, if you put a D4 ring here, just the orbifold, then we have this type of quiver. This is a D4 node, D2-D0 nodes. And this is a perfect matching associated to this divisor. So according to our claim, we have to eliminate these two chiral multiplet as well as this J on the supersymmetric vacua. Then the result is this. And this quiver is related to this type of two-dimensional crystal. And this is known as an orbifold partition. And this was studied by these people about 5 or many years ago. And it's interesting that when you calculate the generating function of the Witten index associated with this quiver and the crystal, then you get this partition function. And this is up to some prefactor. This is proportional to affine SU2 character, and this is consistent with the famous Nakajima's argument about the Ailey space, instantons on Ailey space. Okay, so this is one more example. And we can put a D4 on a different toric divisor of the same Calabi-Yau slipboard. For example, here is a different toric divisor and has a different topology. So if you put a D4 here, then you have a different type of quiver and different type of something happens here, I'm sorry. Different type of diamond model and the perfect matching. Then, according to our claim, we have to eliminate these arrows. Then the result is like this. We have a different quiver and different dimer and, different perfect matching and a different crystal. So we have a different partition function. And this is related to an U1 instanton partition function on this divisor and consistent with physics. And we can also show that this is consistent with the wall crossing formula. Okay, so this is an example. Okay, so yeah, this is the final slide. Okay, thank you. Okay, so let me summarize. So we constructed two-dimensional crystal melting models counting BPS D4-D2-D0 states on a toric Calabi-Yau singularities. And our crystal is a two-dimensional slope or slope face of the three-dimensional crystal associated with D6-D2-D0 counting. And these are what I didn't talk about today, but each molten crystal corresponds to a torus fixed point of the quiver moduli space. And in examples, we checked the consistency with the wall crossing formula. And as I said in the previous slide, if you choose a different divisor to put a D4 brain, then you have a different two-dimensional crystal. So that's it. Thank you very much.
Great talk.
Oh, thank you.
I really like it. And
Okay.
Don't worry about the fact that people appreciate it. Just one question,
Okay.
which is that I got my PhD in condensed matter physics,
Okay.
and that I worked with different type of lattices, including Frappé lattice. You know, like a Frappé lattice.
I'm not quite sure. I'm sorry.
Well, it's a three-dimensional type of lattice. It's very, very special. But if you were trying to melt something like a Frappé, another type of lattice, go back to your prior slide.
Okay.
Yeah, right over there, you're melting crystals. How would you incorporate this, say, for a specific type of lattice? Okay, you did this with respect to a very idealized system. If you're going to put in, your cubes and everything for a, something like a rhombic or a tetrahedral or a Frappé lattice, how would you do that?
I'm not quite sure, but actually there is a paper about the rhombus and.
Yeah, rhombus would be the easiest one.
Yeah, actually this diamond model is closely related to that rhombus styling of the torus, so probably it could be related to. But I'm sorry, I'm not quite sure. So let me discuss it later. Yeah, I'm not quite sure the crystal actually. I just studied the topological string.
Yeah, but
so.
I'm thinking in terms of the big cube and the small cube and all that, is that if you it's very close to the generalization of your C2 T plus C. It's just that you may have an additional term which we put in.
Additional term?
I'm not exactly certain.
Okay. Sorry, I'm not quite familiar. So let me discuss it later. So please tell me, I'm not quite sure the crystal. So I guess you're more familiar.
You an email and ask it to you very specifically.
Okay.
I think, like the rhombic, structure would be the easiest one to generalize that.
Oh, really?
But
Okay. Thank you for
So let's thank Takahiro again.
Thank you so much.